Hello, hello, hello. Today I'm going to discuss with you the solution of that intriguing yo-yo problem. I attach a string to the inner disc of a yo-yo and I pull to the right. If the angle that the string makes with the horizontal is low, the yo-yo will roll in the direction that I pull. If the angle is large, the yo-yo will roll in the opposite direction. I've demonstrated that when I posted the problem, and I would like you to actually do that experiment for yourself. And so the question is, what is that critical angle below which the yo-yo rolls in the direction that I pull, above which the yo-yo rolls in the opposite direction? So let's look at this drawing. You see here the yo-yo, inner radius R1, the inner disc, outer radius R2. I pull at an angle beta with the horizontal. I don't call this alpha because alpha we always reserve for the angular acceleration. So this angle is beta and the tension in the string is T. There is friction with the floor, so there will be a frictional force F in this direction. So relative to the center of mass, to the center here, there is a clockwise torque due to this force with this radius, and magnitude is Fr2, and there is a counterclockwise torque due to this torque, this radius is R1. This is the magnitude of that torque. And that's the factorial sum of the two is I alpha. I is the moment of inertia for rotation about this point, and alpha is the derivative d omega dt, and omega is the angular velocity, this is the angular acceleration. When the system is in pure roll conditions, it means that when it makes one complete rotation, 2 pi r, that the center of mass has moved over a distance 2 pi r. That's equivalent to saying that the velocity of the center of mass is omega r2. Check that if you have forgotten about that. I take the derivative of this, so the v center of mass becomes acceleration of the center of mass, that is alpha times r2. I will drop the center of mass in what follows. Whenever I say A, it's always the acceleration of the center of mass in this direction. I revisit this equation and I substitute this alpha in here, so alpha becomes A divided by R2, and you see that here. In the horizontal direction, F equals ma, m being the total mass of the whole system. T cosine beta is in this direction, and F is in this direction. So T cosine beta minus F equals ma. I combine these two equations, and that immediately gives you this. You can confirm that that's, of course, trivial mass. Now I'm going to bring the a's to one side, and so to speak, solve for A. So this ma term goes here, and then I solve for A. So let's look now at this result. So here then is the result for A. High school algebra, totally trivial. However, it's very interesting. Notice that the sign of A has nothing to do with the bottom part, because the bottom part is always positive. So it all depends on what the top is doing. So I doesn't enter into it, T doesn't enter into it. All that matters is what this is doing. If A is positive, that means if this is positive, the acceleration is in this direction, and so it will roll in this direction. If A is negative, that means this is negative, the yo-yo will roll in this direction. And so, when R2 cosine beta minus R1 is larger than 0, then this is always positive, A is in this direction, and the cosine of beta is R1 over R2. That R1 over R2, the cosine of that angle, beta, is what I call the critical value for beta. If cosine R2 cosine beta minus R1 is smaller than 0, then the cosine of beta is less than R1 over R2, and then the acceleration will be in this direction, so the yo-yo will roll in the opposite direction that I pull. Let's take an example. We take R2 over R1 is 2, then the critical angle beta is 60 degrees. So if the angle beta is lower than 60 degrees, it will roll in the direction that I pull. If the angle of beta is larger than 60 degrees, it will go in the opposite direction. Let's do another trivial consistency check. If we make beta 0, then the cosine of beta is 1. Then R2 minus R1 is always larger than 0 because R2 is larger than R1. So it will always roll in the direction that I pull. If beta is 90 degrees, then the cosine of beta is 0. So A is determined then by this minus R1. So A is always negative and it will always roll in this direction. So, in a sense, the problem has now been solved. However, I want to discuss with you what I call a miracle solution. So let's take a look at my miracle solution. And in a miracle solution, I'm making use of something that I have never proven to you, and I'm not planning to prove it. But you can check it on Google or you can try to prove it for yourself. If an object is rolling and if it is in pure roll condition, then at all moments in time, the point of contact with the table stands still. And if the angular velocity of rotation about the center of mass is omega, then the net result is that the entire object, in this case the entire yo-yo, is then rotating about that contact point with the desk, I call that point P, with that same angular velocity omega. It's not so trivial that that is true, but I will show you two consistency arguments. That doesn't prove it's right, but at least it has to pass that consistency. So I claim then, if this object is rotating with angular velocity omega about the center of mass, that is a pure roll condition, that's equivalent to this point P always standing still. Of course, a little later in time, it will be a different point that will be point P. But at a particular moment in time, this point stands still, and the entire unit is now rotating about this point with angular velocity omega. Use the center of mass. In pure roll, we know that the center of mass has a velocity omega r, and this is r. So that velocity, if we use P as the origin of rotation, and the whole thing rotates with angular velocity omega, then this velocity is this r times omega, which indeed is omega r2. This is r2. This point is a distance from P which is 2r. So it means that this point must have a velocity then of 2 omega r2. And that is obvious that it has that velocity, because in the rotating frame at the surface here, every point has a velocity omega r2. But since the center of mass itself is moving with velocity omega r2, this point is the factorial sum of both velocities, and so it must become 2 omega r2. If we take point P itself, the distance from point P to point P is 0. So that's consistent with the fact that it must stand still, because omega times 0 is 0. If we choose a point at the circumference here, which has a distance r from point P, then the velocity of that point here is perpendicular to this line, would be omega times small r if this distance is small r. So you can pick any point the point doesn't have to be at the circumference. It could be here, it could be here, it could be there, it could be there. The concept that its linear velocity is always omega times the distance from point P to that point. So I'm going to use that for my miracle solution. I draw here a tension, the rope, so that the rope goes through point P, the extension of the rope. Because the rope starts here, but this is the extension of the rope, goes through point P. This angle is then the critical angle. Because look, in this triangle, this angle beta here is the same as this angle. And the cosine of this angle is R1 divided by R2. So if I put the string in such a direction that the extension goes through P, that angle is then the critical angle. Now I'm going to make the angle beta smaller than this critical angle, which is this blue line. And now it ends up here. It ends up on the left side of point P. If it ends up on the left side of point P, that will cause a clockwise torque. There is no torque relative due to this force F at the bottom, because F and R are in the same direction. So that torque is zero. So the only torque that we have is then due to this tension and this distance. And that's a clockwise torque. So if it's a clockwise torque, since it's rotating about point P, if you accept that concept, it must rotate to the right. If you make the angle larger than beta critical, then the tension is in this direction. So relative to point P, there is now a counterclockwise torque. And since we just accepted the notion that it is equivalent to a rotation about point P with angular velocity omega, this torque will now make it rotate in this direction about point P, and so it will roll in the opposite direction. So this miracle solution requires almost no mass, which I needed before. And it's visually very pleasing. I like this very much. Of course, the question now is, what would happen if you pull exactly in the direction of beta critical? Right? Try to answer that, but don't bother me, okay? All we know is if the angle is smaller, it rotates in the direction that I pull, and if the angle is larger, it rotates in the other direction. So you have to conclude then that if the rope, the extension of the rope, goes through point P, that it won't even rotate. And that's the correct solution. The correct answer. Okay, this was not an easy problem, I realize that. Take care, have a nice day, and try to be still friends, okay?